In this talk, I'll give a quick overview of an analysis we did where we tried to analyze the KiDS-1000 gravitational lensing results with a cross correlation between gravitational lensing and the tSZ effect. Jump right in. Gravitational lensing, we can think of as a quite analogous picture as of trying to infer the surface of a pool by looking just at distortions of the tiles at the bottom of the pool and the specks of light. Now, we obviously don't look into pools when we do cosmology, we look into telescopes of the sky. So a slightly more practical illustration is if you have faraway galaxies that are circular in shape, for example, a spiral galaxy that you look on and face on, as that circular image traverses around the universe towards you, towards the telescope, then that light gets deflected as it passes by mass distributions. And if that deflection is small, then the resulting effect on the circular image is that it gets distorted into an ellipse. And looking at how different or large number of galaxies are distorted in that manner can make some inference on how matter is distributed in the foreground. Now, there's a different way you can measure this. One particular ways that's very often used in cosmology these days is called cosmic shear, which is a two-point statistic. So we look at correlation between galaxy shapes. And the neat thing about cosmic shear is that it probes the distribution of all matter, suppose dark matter and baryonic matter. But we don't, for example, have to do this galaxy and galaxy bias. Now, going back to the previous picture, if you have our catalog of observed galaxies with their shape measured, then to measure cosmic shear, we measure the correlation between all pairs of galaxies. We measure the pair of first galaxies, the shape, we correlate the shapes of another pair, and we do it for all pairs in our survey. Now, the data we actually use to do that, in this case, is called KiDS-1000. So KiDS stands for the kilodegree survey, and that's a wide-field optical survey optimized for weak lensing. The data I'm presenting here correspond to 1,000 square degrees. The full survey will be slightly larger, and we're using about 20 million galaxies for the present analysis. What sets KiDS apart from other current stage 3 survey like the dark energy survey or HC is that we have full coverage with infrared survey called Viking. So we have 9 photometric bands for our galaxies, which gives us quite confidence in the estimate of our photometric redshifts. Speaking of tomographic redshifts, I said before, as light travels from these galaxies far away, the light gets deflected. So if you split up the galaxies, depending on distance to us, then you get population of galaxies that are more distorted and less distorted, depending on how far they were away. Shown here in the top, the different colors correspond to the different splits we divide our galaxy population in. And the bottom shows the effective gravitational lensing effect from these source distributions. And you see that the source distribution that is furthest away, so the highest redshift pose, has the largest gravitational lensing effect because there's more matter between us and these galaxies that can be causing these distortions, but also if they probe the matter distribution at higher redshift, so from structures early in the universe. And by combining these different redshifts, we can learn something about how structure evolves with time. What it looks like in practice, so what's shown here is a measurement of the cosmic shear signal in KiDS-1000. Specifically, what's shown here is called a angular power spectrum. So instead of measuring correlation functions, it's basically the Fourier domain analog to that. Again, we have our 5 redshift bins. So the highest redshift bin again has the most gravitational lensing. See quite a nice signal. And as you go to lower redshift, the signal becomes weaker and more noise dominated. And the lower triangle here is all the cross correlation between these tomographic bins. Give some intuition on what this power spectrum means in terms of what kind of structure that these signals correspond to. use a toy model. So on the left is shown just a Gaussian random field corresponding to the angular power spectrum shown here on the right. So the x-axis here is multiple, denoted as L, and the y-axis is the angular power spectrum. And to begin with is just a constant power spectrum, which corresponds to white noise in the field. Now, as you increase power on large scales compared to power on small scales, you see these structures emerge from the noise. And as the power then decreases on large scales, corresponding to small l compared to the small scales at high L, we come back to the case of white noise field. Now, obviously, our models are more complicated than just the power laws. We account for the whole Boltzmann solving for the linear matter distribution. We add harmonic feedback, intrinsic lambda, and so on. So using that model, as well as the data I just showed earlier, we can derive cosmological constraints for this parameter that the model depends on. So here I shown the constraints from KiDS-1000 cosmic shear for a parameter called sigma 8, which measures how clumpy matter is, and a parameter called omega m, which measures how much matter there is. And you can see there's this degeneracy as both more matter that's less clumpy and less matter that's more clumpy, both have quite similar big-cleansing signals. But across this degeneracy, so the parameter combination called S8, we have quite good constraints. And across this degeneracy, there's some difference with what the primary CMP says, so what's analyzed by the Planck collaboration. Now you can argue about if that difference is significant or not. But it might be interesting that such a difference exists in the first place. One of the reasons, called baryon feedback, I'll try to get to in the rest of this talk. Now all the gory details are listed in this list of papers that we put out about 2 years ago on the KiDS-1000 analysis. So if you have any questions about the details, I invite you to have a look at this collection of papers. But coming back to cosmic shear and baryons, as I mentioned, cosmic shear probes the distribution of all matter. That includes both dark matter and baryons. And most of the baryons is in the form of gas, and only a small fraction of that is actually in stars and galaxies. So what we actually can see in the sky is about 10% of all baryons, which is only about 15% of all matter. Now, why is that a problem? If you look at simulation of dark matter versus simulation of dark matter plus baryons, so including galaxy formation, then we see the left, dark matter just collapses almost serenely under gravity, while on the right here we have fireworks going off from all kinds of very nonlinear processes like supernovae, like feedback from supermassive black holes called EGN feedback. So clearly what's going on here on the right is much more complicated than just gravitational collapse that dark matter undergoes. And this is somewhat of a problem. If you go to different simulation groups and ask how is all matter the matter distributed in their simulations, measured here in terms of the power spectrum, so how much variance is there in the matter distribution at different scales, and they come up with quite different answers. What's shown here is the ratio between the power spectrum from simulations that have both dark matter and galaxy formation over the power spectrum from just dark matter, and you see that while there's an overall similar shape and that there's suppression of power on small scales because these highly energetic processes like EGN feedback blow gas out of halos, there's quite some differences in the details. And it's somewhat troubling because that's exactly the quantity that goes into computing the prediction for our gravitational lensing signal. We then use to infer things like sigma and omega n. So if we get this wrong, this might be one of the reasons why the cosmic shear results don't line up with what Planck predicts. Now we thought, well, one of the reasons this pressure of power occurs is because gas gets pushed around by these baryon processes. So can we map out where gas is, and can we relate that how to where the dark matter and the rest of the matter is distributed? And one way to do this is using something called the Sunyaev-Zel'dovich effect. And that basically comes about when you have low energy photons from the CMB that get inverse Kopplung scattered by ionized gas, just having free electrons and getting scattered of those. And that causes basically the low energy photons to get a slight kick, and that changes the black body spectrum of the CMB. So if you look at the spectrum of the CMB at different places on the sky, that you can see this small shifts. And if you map out the shifts, this gives you essentially a map of where the hot gas is. Or precisely, it gives you a measure of the electron pressure throughout the universe, which is almost what we look for. What we did is we used that map, this tSZ map, to map out where the electron is and how hot the electrons are, and correlate that with the shape of background galaxies. So correlated with gravitational lensing. So this is a correlation between gas and the shear induced by the same structures or similar structures that the gas resides in. So to summarize, this shear tSZ cross correlation is a cross correlation between galaxy shapes and the tSZ effect. And it probes both the distribution of matter through gravitational lensing and distribution and temperature of gas through the tSZ effect. As data for this tSZ effect, we have two data sets. We have Planck, which gives us full sky maps. The downside is that the resolution is quite poor because Planck has a 10 Arcman beam about. On the other hand, we have the Akadama Cosmology telescope, which has a much better angular resolution, but only part of the sky is measured, and that part only overlaps partially with our KiDS data. So the overlap area is quite a bit smaller than with Planck, but angular resolution is much better. Now what I'm showing here is the actual cross correlation measurement, again in terms of angular power spectrum between our Planck Z map and KiDS-1000. And as you can see, we get a quite nice signal. It's about a 9 sigma detection. And again, on higher redshift, shown as S5 here, you have a stronger signal than for the galaxy population at lower redshift. Now, for the modeling, we use something called HMX. That's work mostly done by Alexander Mead. And HMX is a halo model based approach. It's somewhat logical, but it has a quite physical underlying principle. And it models different components separately. So we have a dark matter component, we have a gas component, we have star components, and so on. And all of these components have their own parameters, like how puffy the dark matter halos are, for example. And we calibrate all these components on the Bahamas suite of hydrodynamical simulations. There's simulations that include galaxy formation, HN feedback. And the neat thing is that Bahamas provides simulations at different feedback strengths. So we can fit our halo model at these different feedback strengths, and then basically relate these internal parameters to an overall feedback strength parameter, so that we end up with a model that can coherently predict both the matter distribution and the cross correlation between matter and gas with basically a single baryonic feedback parameter. So then we can plot this model prediction against the actual data, and then, for example, vary the strengths of HN feedback. So it's shown here for the range of scales we use. If you increase the feedback, that essentially causes just a suppression of power because gas gets expelled out of halos. But because it has an underlying halo model, we can also change the cosmology, like sigma 8, omega m. And then we run a full Bayesian analysis to infer both cosmology and baryonic feedback streams. Shown here again, it's the same parameters shown before, so sigma 8 and omega m. And this is a lot more sensitive to sigma 8 than cosmic shear because the tSZ signal is more sensitive to this parameter because it essentially probes big clusters, big heavy halos, and those are more abundant when there is more clustering, so sigma 8. Now, as said, we did a joint analysis, so we combine and the cosmic shear results shown here in the bottom left that I showed before, and the cross correlation between the shear and the tSZ effect shown at top right, and we account for the full covariance between those measurements, and then we get combined constraints. And the neat thing is because we have this cosmic shear banana in blue, that may be a shear tSZ cross correlation potato, because these have different degeneracy. Combining these two probes breaks these degeneracies, and we get much better constraints in either of these probes on these parameters. And again, just to orient where that listed parameter space here in red is again Planck constraints. So this combined joint analysis can really change the overall picture. So the discrepancy or agreement, however you want to call it, between Planck and our result is still at about 2 sigma level. Now to the baryonic feedback parameter shown here in blue is the cosmic shear constraints or lack thereof, and that's on by design because we designed the cosmic shear scale cuts such that we are not sensitive to these nonlinear scales that are affected by baryonic feedback. And then the cross correlation constraints are orange. The reason why they're not much better is that we use the same scale cuts as for cosmic shear to enable this joint analysis, but at shooting us ourselves a bit in the foot because we essentially throw away the skills that we are interested in for this kind of analysis. And in green is the joint analysis of the two, and that leads us right back to where the Bahamas simulations think that feedback should be, and that's because the simulations have been calibrated at other observables like the galaxy stellar mass function or the gas fractions in groups and clusters. It's reassuring that we end up with similar results than what the Bahamas people found. And I'll leave it at that, and I'm happy to take questions in the discussion session. Thank you very much.